Okay. Hello, everyone. My name is Darian, and I'm going to be talking to you about NodeMedic-FINE. This is joint work with my colleagues at CMU and IST. I'll start by introducing Node.js, a JavaScript runtime that brings JavaScript out of the browser and enables developers to use JavaScript for client-side, server-side, desktop, and IoT development. Because of this, as well as its large ecosystem of packages, Node.js consistently ranks as the top web framework in Stack Overflow's developer surveys, with over 40% of respondents saying that they use Node.js in their day-to-day work in 2024. Unfortunately, Node.js has a number of privileged APIs whose misuse often leads to vulnerabilities. JavaScript itself provides dangerous APIs for dynamic code evaluation, such as eval and new function. If not used correctly, an attacker-controlled string input reaching eval will be executed as JavaScript code, enabling a variety of attacks. This is called arbitrary code execution, or ACE. Node.js additionally provides APIs for operating system level command execution, such as exec and spawn. If misused, an attacker-controlled string reaching exec can be interpreted as shellcode, enabling an attacker to run arbitrary commands on the host operating system. This is called arbitrary command injection, or ACI. ACE and ACI are the primary vulnerabilities we examine in this work because of their severity. An attacker who can perform ACE and ACI can also perform weaker attacks, like directory traversal by extension. Let's now look at the anatomy of a real-world Node.js package vulnerability, the Node.js package font converter, which had over 8,000 downloads before we reported the vulnerability. If we look at this source code snippet at the site of the vulnerability, we can see that the package's convert API takes a font file source and destination, and then uses the source, unsanitized, to construct a command string that is then passed directly to exec. We can perform dynamic taint analysis, a type of data flow analysis that tracks the flow of attacker-controllable values through the code to reveal a tainted flow. The SRC source flows to the exec sync, indicating an ACI vulnerability. If the user can control the font file, then they can submit a file name containing a shell command that will be executed on the server running this package. This vulnerability was assigned a CVE with a CVSS score of 9.8, indicating critical severity. We can break the process of vulnerability identification into two steps. First, detection of a tainted flow. We call these initial tainted flows potential flows because they may not be vulnerable, for example, due to the program rejecting malicious inputs. Second, we then need to confirm the flow by creating a proof of concept exploit that demonstrates the vulnerability. For automated detection, one key challenge is performing precise yet scalable taint analysis. This was investigated in depth by our prior work NodeMedic, as well as Affogato, ICNIA, and many others which performed dynamic taint analysis. The next challenge, for dynamic analysis specifically, is ensuring that the package is correctly invoked and thoroughly explored. Prior work such as JSFuzz investigated effective JavaScript-specific fuzzing techniques, but was limited to string input generation. In NodeMedic-FINE, we've developed a fuzzing methodology that performs reconstruction of the diverse input types, strings, objects, arrays, numbers, that Node.js packages expect. The final challenge, when automatically confirming a flow, is ensuring that a syntactically and semantically valid proof of concept exploit can be created. Prior work, such as FAST, used constraint solving to generate valid exploits, but the constraints come from static analysis that is limited in modeling built-in functions, leading to false negatives. In NodeMedic-FINE, we synthesize exploits using constraints gathered from runtime execution traces to boost confirmation rates. Let's now look at our architecture for delivering these two contributions. NodeMedic-FINE starts by ingesting a Node.js package and generating a driver that can automatically execute the public APIs of that package with provided tainted inputs. The driver, as well as the package, are instrumented to perform a type of taint analysis called provenance analysis. The instrumented package and driver are given to our fuzzer, which performs type sampling and object reconstruction to generate inputs and execute them on the package running on Node.js. The result of this, if a potential flow is found, is a provenance graph which stores a tainted flow in the form of a trace of operations performed on the tainted data on its way to the sensitive API sink. At this point, detection of a potential flow is done, and we move to confirmation of the flow. We give this provenance graph to our synthesis engine, which uses a combination of techniques to produce a synthesized proof-of-concept exploit. This exploit is then injected into the driver, which is then used to execute the exploit on the package. We can then concretely see if the exploit was successful, automatically confirming the flow. The first two steps of this pipeline, as well as the core synthesis engine, were developed by our prior work, NodeMedic. The fuzzer and the additional synthesis methodology are novel, and we'll dive into them next. At a high level, we implement coverage-guided type and structure-aware fuzzing of the package to explore more of its execution paths. The fuzzer relies on two core techniques, the first of which is type sampling. The fuzzer maintains a list of JavaScript types that it has tried. For each one, it keeps track of how many times the type was sampled and associates a reward based on coverage, lines of additional code, that the type caused the execution of. The key observation is that types that were found to be effective at increasing coverage are more likely to be chosen when generating subsequent inputs. The second core technique is object reconstruction. The fuzzer additionally maintains a JavaScript structure specification that keeps track of fields that the package's input object is expected to have. The way that this works is that we've instrumented object field access such that when we execute the package, we get back feedback that both indicates additional lines covered by the type, as well as discovered object fields, here a field called filename. The feedback is used to update the sampled, reward, and structure fields of the specification. The reward is then used to guide the creation of a new input using the updated specification. These two mechanisms, type sampling and object reconstruction, enable the fuzzer to reproduce rich inputs for a package that achieve higher code coverage and thus uncover more potential flows. Let's now shift gears and look at our confirmation methodology, starting from a provenance graph. I'll use the example of a toy package that simply runs grep on a substring of an inputs field. At the bottom, you can see that we generate a simple driver for this package that calls the grep API with tainted input from the fuzzer. The result of analyzing this package with our provenance analysis will be a provenance graph, an actual example of which is shown on the right. I'll go over the key details of the provenance graph, so no need to try to read it. The provenance graph is a data structure that stores a trace of operations performed on tainted data during a dynamic execution of the program. At the top of the provenance graph, we have the tainted source input, and at the bottom, we have the sync function exec. Nodes are numbered in reverse data flow order. We can see the correspondence between fields of the provenance graph and code within this toy package. First, we see the call to grep with a fuzzer input. Next, we see that the file name field of the input is accessed, and a substring of that field is taken from characters 5 to 25. The result of that is concatenated with the literal string grep and then passed to exec. We use the provenance graph for exploit synthesis with the insight that operations in the provenance graph allow us to infer the required type and structure of a POC input and constrain its payload. First, we convert the provenance graph into an SMTlib formula that encodes the graph's JavaScript operations as well as our desired POC payload. We first declare a symbolic field that we're solving for, the file name field, and assert that a substring of that field from index 5 to 25, concatenated with grep, will contain our payload that must reach exec. Here, just shellcode, executing the command touch success. Next, we solve this with the SMT solver Z3, and if the formula is satisfiable, which it is, we derive a model that gives us a satisfying assignment to the symbolic field. Here, our exploit payload with 5 random characters at the beginning, since the first 5 characters of the string will be cut off by the substring operation. Then, we generate an input structure, which we have separately inferred based on the structure of the provenance graph to be an object with a field called filename, and we insert the payload as that field's value. Finally, we execute the POC input on the package API and check to see if it is successful, which it is, as evidenced by the creation of a file called success on the host machine. Okay, so we've now seen how NodeMedic-FINE works. Let's take a look at how it performs in practice compared to our prior Node.js dynamic taint analysis, NodeMedic. In our previous paper, NodeMedic analyzed 10,000 packages randomly selected from NPM, finding over 150 tainted flows, of which 108 could be automatically confirmed. With NodeMedic-FINE, we've expanded the dataset to include all packages from NPM with more than 0 downloads that passed our filters, such as checking for the ACE or ACI syncs that we analyze, for a total of about 33,000 packages. NodeMedic-FINE is able to uncover 2,257 potential flows, of which the majority are ACI, and is able to automatically confirm 612 ACI flows, as well as 154 ACE flows, for a total of 766 automatically confirmed flows. We've reported the resulting vulnerabilities to developers, and over 50 have been confirmed so far, with 35 now patched. To understand the contribution of key components of our infrastructure, we also performed an ablation study. We found that our fuzzer is responsible for a 1.7x increase in potential flows, with per-type rewards and reconstructing input structure contributing the majority of the increase. And our synthesis engine is responsible for a 1.6x increase in confirmed flows, with type and structure guidance contributing the majority of the increase. Finally, we compared against FAST, a state-of-the-art static analysis that also automatically confirmed flows. We compared performance on the SecBench.js benchmark dataset, looking at counts of automatically confirmed ACI and ACE flows. We find that NodeMedic-FINE and FAST are very close when it comes to automatically confirming ACI flows, with NodeMedic-FINE pulling out slightly ahead when it comes to the confirmation of ACE flows. Finally, I'll conclude by saying that there is much more to see in the paper in our repository, so please take a look. In the paper, we have explanations of the enumerator we use for generating ACE payloads, our type and structure inference methodology for synthesis, and additional evaluation details. In our repo, we have our complete gathering analysis pipeline along with ACI and ACE case studies that can also be found in our artifact appendix, for which we have received the available and functional badges. Thank you so much for your time and attention.
Thanks. Any question?
Yeah, thank you very much for your talk. Very interesting work. So I have a question about the provenance graph. So
Sure.
Once you have there some operations that are not standard built in JavaScript, assuming you're calling a package or something, how do you translate that to the Z3 constraints?
That's a great question. So what we've done is we've created a set of SMT-lib models corresponding to these JavaScript operations. And we first performed a kind of survey of packages and the common operations they used to gather what the top operations would be. And we created precise models for those. And then we have a way for the less precise ones to just kind of treat them in almost an uninterpreted way. OK.
And can you give us an estimate how common these things are? Like how often you needed to use the models or how many models you have?
Yeah, so we need models at the SMT-lib level for all of the built-in operations that JavaScript has, like most commonly string operations. Like when you perform substring, concatenation, any of these operations, we need to create a corresponding model. Sometimes the semantics of the JavaScript operation align pretty much exactly with what Z3 has in the SMT-lib specification. But other times there are subtle differences in semantics that require us to produce our own model using the Z3 equivalent operations to reflect the semantics of JavaScript.
OK, thank you.
Yeah. Thank you for the question.
Time for another question. Maybe stepping back a little, so you show us something for exploit generation. Do you think it can be useful outside of JavaScript? Or is it really tailored to JavaScript?
Yeah, that's a great question. I think fundamentally there is something in the methodology that can be applied in other places, but there would need to be a bit of legwork done to get it to work in other situations. Essentially, what our approach relies on is the creation of this provenance graph, right, that encodes the operations during a dynamic taint analysis of some program. So if you're running in a different runtime, say in Python, and you can also produce a provenance graph, then you can also leverage what we have for exploit synthesis, assuming you also adapt the SMT-lib models to reflect Python semantics rather than the JavaScript semantics.
Okay, so let's thank the speaker again.
Thank you.